I will tell you a terrible thing now. Nuclear spin isn't actually spin. Not in the sense that we've discussed in the previous lecture. Instead, it's the total angular momentum of the nuclear ground state. And this lecture is about what exactly I mean by that statement. So, we are diving inside the nucleus today. There are plenty of things that chemists and to some extent physicists are never told in their undergraduate courses. In your undergraduate modules, nucleus is a massive point charge somewhere without any structure to it. That is, of course, untrue. It does have a structure, and the structure is very consequential. Firstly, the size scale. A typical nucleus is a few femtometers across. A femtometer is 10 to the minus 15th meters. So typical chemical length scale is 1 angstrom, right, 10 to the minus 10th meter. And the reason chemists like angstroms is because 1 angstrom is almost exactly the length of a CH bond. And that gives chemists an immediate structural intuition. You say that some molecule is 5 angstroms across. Well, that's immediately 5 CH bonds across, which is an immediate visual reference for what is happening in there. But 1 angstrom is 10 to the minus 10, 1 femtometer is 10 to the minus 15th. So a nucleus is 5 orders of magnitude smaller than a typical chemical bond. Secondly, it's not a hard sphere. Its surface is in fact quite fuzzy. If you look at a database that particle physicists maintain called Nuclear Charge Density Archive, you will see that, well, it's a bit fuzzy on the surface, and some of them have those little hollow bits inside, so the charge distribution is non-trivial. Secondly, nuclei are certainly not spherical. There are egg-shaped nuclei, there are mango-shaped nuclei. In certain excited states, there are heart-shaped nuclei. So nucleus has a shape. If you go into high energy excited states of nuclei, they can have angular momentum, actual literal mechanical angular momentum. You can spin a nucleus up and down. In collision experiments, if you have a collision that's not head-on or somewhat sliding incidents, you can populate high angular momentum states of nuclei to the total quantum numbers, which are completely crazy. You can spin up, this is the famous erbium-158, to a point when a few nucleons detach from the bulk, and the whole thing is described by this review as not dissimilar to the rings on Saturn. And as you are spinning it up further and further, the whole thing loses mechanical stability and flies apart. So nucleus really does have internal structure. Even ground states of nuclei come in a variety of interesting shapes, and all of this is interesting enough that a Nobel Prize was awarded for this in 1975. So our mission today is to take a look at what goes on inside the nucleus. And for that, I need to take you back to what you already know about electrons. So reminder, flashback, what we did to an electron in a hydrogen atom. Well, you know that in the Hamiltonian of an electron nucleus system, we've got the nucleus mechanical momentum, you've got the electron momentum, and you just have the Coulomb interaction between them. And then the Born-Oppenheimer approximation says, well, nucleus moves significantly slower than the electron. Why don't we move the center of mass to coincide with the center of mass of the entire system? Then we've got the reduced mass for the momentum, and we only have the electron position relative to the nucleus, and everything else we can approximately just subtract out as an energy reference. And this is the Born-Oppenheimer approximation. And then what we did was to plug this into Schrödinger's equation. We did the usual variable separation trick when we took the total electron wave function, separated into a product of a radial part and an angular part, plugged it into there, translated the Laplacian into spherical coordinates, split it up, produced these horrible equations which makes a chemist's eyes glaze when I derive all of that to them in their second year calculus course. Then you're separating it into the radial part and the angular part, and all the quantum numbers. So the principal quantum number lives here, the orbital and the magnetic quantum number lives there, and this is your standard orbital classification. So you've got 1, 2, 3, 4, 5. You then have s, p, d, and f orbitals, and the magnetic quantum number gives you the slots inside each individual orbitals. This is how we did it for the electron. Now, what about the nucleus? What holds the nucleons together? It's not Coulomb interaction. Of course, the nucleus would have flown apart, right, because of the repulsion. If the Coulomb interaction was strong enough. No, this is something much stronger. This is called strong nuclear force. It's very short range, so roughly 1 femtometer, about 100 times stronger than electromagnetic interaction, so it can keep the nucleus together. It has the same relationship with the strong force between quarks as van der Waals interaction has with Coulomb interaction. So it's a perturbative sticky residue of the strong force between the quarks. Its potential is unknown to this day, but mathematically it must exist, and its symmetry is pretty close to central symmetry, so we can use the same group theory as we have used for the hydrogen atom. Well, let us try. Okay, let's write a single nucleon Schrödinger's equation. Let's take a nucleus with, I don't know, just one unpaired nucleon. What we must have there is the usual momentum term for that nucleon. That's the mass, that's the Laplacian, and some kind of mean field potential of that nucleon in the collective strong force field of all the other nucleons. So single particle Schrödinger-like equation for a confined nucleon inside the nucleus. Well, same old Laplacian, right? We can split it into radial and angular part. We don't know what this potential is, but it's pretty likely it could be center symmetric. So it's a function of the radius, but not the angle. So it ends up in the radial part. And at that point, the angular part is exactly the same as what we had in the hydrogen atom. And so, of course, all the angular classification of nuclear orbitals is then inherited from the hydrogen atom. You have an s orbital, p orbital, d orbital, and so on inside the nucleus. And what lives in them is protons and neutrons. And the strategy will be, in order to find the plausible description for this, is to look for what's called magic numbers. Remember the population numbers of electrons that corresponded to helium, neon, argon, krypton, xenon, right? They were closed shells that were chemically inert. There are similar things for nuclei. Certain nuclei are particularly stable. And those are those with these numbers of nucleons empirically, either protons or neutrons. So let us try and find a potential and some extra things on top, as we shall see, that would explain the extra stability attained by the nuclei that contain this number of protons or neutrons. And, well, one particularly successful potential is essentially just a square well with rounded edges, the Woods-Saxon potential it's called, which simply is just a finite restraining potential for neutrons, and for protons the floor is slightly higher because protons additionally repel each other through the Coulomb interaction. So why don't we use this and take a look at what is going to happen. So, if we put a nucleon into just an infinite square well, we do get energy levels, like for any particle in an infinite square well, but they absolutely don't match the observed magic numbers of nucleons. We can do slightly better and do a finite square well, and they still don't match. We can do this square well with rounded edges, and they sort of begin to vaguely match, but not quite yet. And to chemists, this looks wild, and this looks wild because this looks a bit silly, right? In the hydrogen atom, one d orbital did not exist. It couldn't have existed. But in a nucleus it does, and this is because the physicists are silly. They didn't number them properly like we number them for hydrogen atoms. They literally just numbered them in the order of appearance. So the first d-like orbital that they encounter up the ladder is called 1d. even though it actually turns up from the second excitation. All right, the first p orbital is 1p, and the first f orbital is 1f. So this is literally just in the order of appearance, vertically up. So there's no physical, well, there is a physical meaning, this indicates the symmetry, but the principal quantum number has no meaning here, unlike for the hydrogen atom. Secondly, we can have h orbitals and I orbitals inside nuclei, so stupidly high angular momentum quantum numbers of the kinds that do not occur in hydrogen-like atoms in periodic table. And thirdly, these energy gaps are giant, right? These are mega electron volts. These are the gaps that a chemical system has no realistic chance of ever traversing. You have to hit your nucleus with a gamma ray for something like that to get excited. And these excitations are really short-lived, like femtoseconds or even shorter. And spinach can solve nuclear structures for single nucleon atoms. That's the Woods-Saxon potential in 3D for charge 20. And if you start calculating the eigenfunctions of the Schrödinger-like equation in this potential, that's your S-like orbital, that's your P-like orbital, that's your D-like orbital, and as you can see, they're all packed inside this sphere a few femtometers across inside the nuclei. So nucleus has a structure which is vaguely similar to what chemists have already seen for a hydrogen-like atom, with these significant differences. The second thing that is very different, and now I am flashing back to electrons. So the second very different thing is spin-orbit coupling. Remember what we had for the electron. Well, we've just had the previous lecture on the subject, right? So this LS coupling. But if you look at this number in here, here's the minus, and the electron charge is negative, so this is a plus. And so this number here is positive, which means that collinear orientations of electron and of orbital and spin angular momentum are higher in energy, right? So the electron couples to the orbital angular momentum for the smallest total for the hydrogen-like atom. And so, of course, we know all the usual labels, right? S dot L commutes with L squared, commutes with S squared, and commutes with L plus S. So that's the total orbital, that's the total spin, and that's the total in general. And these are the usual atomic term symbols, right? That's the spin multiplicity, that's the J, and that's the L. And anybody of you who did optical spectroscopy will remember those term symbols. And then we can calculate the corresponding energies, and that gives us the spectroscopic multiplets. And that's your usual school kid electronic structure theory. A configuration, for example, for F6, is split by electron repulsion into terms. Spin-orbit coupling splits the terms into multiplets, and then the crystal field splits the multiplets into crystal field states. And parallel L and S orientations are higher in energy because this number is positive. And then, of course, this is the famous zero field splitting. Okay, but again, the entire classification is based on spherical symmetry and spin. Nucleus also has spherical symmetry and spin degrees of freedom in every nucleon. So actually this classification is inherited, but with one significant difference. Nucleons are positively charged. And so the sign of the spin-orbit coupling now is negative. So the ground state is not the minimum total momentum, but the maximum total momentum that turns the ladder upside down for the multiplet splittings inside the nucleus. So parallel L and S orientations are lower in energy inside the nucleus, but exactly the same labels and exactly the same spectroscopy, except we're dealing with gamma ray scale excitations in here. And so this now, see the labels, which are again vaguely familiar to chemists, right? So the first number has no meaning, it's just the order. Second one is the L, and the third one is the projections of the J. And if we look at the natural gaps that occur in this excitation ladder, there's 2, there's a gap at 8, there's a gap at 20, gap at 28, gap at 50. These are the magic numbers that we have. And so nuclear retention in a spherical potential with rounded edges combined with nuclear spin-orbit coupling, which is much stronger than Coulomb interaction, 5 times stronger in fact, predicts these magic numbers. And this is not altogether unfamiliar to you from your previous chemistry courses. Okay, so what the hell then is nuclear spin? Well, let's take a look at carbon-13 and start populating those energy levels. 1s12, there is a proton up and proton down, fully coupled, no overall spin, closed shell. There are 2 neutrons, neutron spin up and neutron spin down. p3 half, there are 2 such orbitals, 4 nucleons here, 4 nucleons here, fully paired up. There is 1 unpaired neutron sitting in a nuclear p orbital with j half. So the total angular momentum of the p orbital with L equals 1 and a neutron with S equals half gives you the J1 half, and this is why carbon-13 has what we then in the textbook call a spin half. This is not spin, this is the total angular momentum. For the nitrogen-15, you have a single unpaired proton sitting in the 1p half. But if you look at things like oxygen-17, let's take a look here. In oxygen-17, you have a single unpaired neutron sitting in a d-like orbital. So remember what I told you, the pairing is for the maximum j. So d contributes L equals 2, and unpaired neutron contributes S equals half. 2 plus a half is 5 halves. So the spin of oxygen-17 is 5 half, but it's actually mostly orbital. Right, 2, L equals 2, is the orbital angular momentum, and only 1 half comes from the unpaired neutron. So we call it spin, but it's not just spin, right? It has significant contributions from the orbital motions of nucleons inside the nucleus. So this is why I told you at the very beginning that nuclear spin is not actually spin. It has orbital contributions. It is not spin in the same sense as the electron spin. However, to us, chemists, we are sitting in the ground state. We never do gamma spectroscopy. For us, this doesn't change. For us, it's a fundamental property. For us, it's as good as spin. Right? We can pretend that it is spin. And well, these are the population diagrams. Interesting thing now, they are two-sided. These are proton populations and these are neutron populations. And you can see neutron energy levels are slightly slower because the neutrons do not repel each other. Protons do, so they push each other higher in energy. And you can see the S halves, both protons and neutrons are populated, P3 half, P1 half, and that's your single unpaired neutron sitting in D5 half. This is why oxygen-17 has a spin 5 half. Likewise for nitrogen-14, unpaired nucleons here, they're both sitting in P half, but they pair for the maximum total angular momentum, so nitrogen-14 has J equals 1. And if it's oxygen-16, everything's nicely paired up, and so there is no uncompensated angular momentum, and so oxygen-16 doesn't have a spin. So this is what nuclear spin really is. Okay, how does this thing, whatever it is, acquire a magnetic moment? Where does the magnetic moment comes from? Well, let's think about it. What we are sitting in is a ground multiplet. These excitations are kilo-electron volts at least. We will never be here. For all intents and purposes, we are in the bottom multiplet. Might just as well project all our operators into that small number of ground state reachable energy levels. Well, there's a Wigner-Eckert theorem in mathematics that if you do that, almost anything ends up being a multiple of the corresponding angular momentum operator. In particular, any operator, when you project it into a J multiplet, becomes a linear combination of angular momentum. Well, for nuclei, we call it spin operators. It can be the magnetic moment. And I will give you here another flashback. So we are back to electronic structure theory. How did we get the magnetic moment of electrons in electron magnetic spectroscopy? How did we get Landau G factor? Well, that's the total magnetic moment, that's the orbital contribution, that's the spin contribution for an electron, We use Wigner-Eckert theorem to project it into the ground J multiplet. I will not bore you with the reminders of all the mathematics you may have seen in your spectroscopy. Good quantum numbers are these, and these. And then we calculate this inner product matrix elements, and a lot of mathematics later we get the expression for the Landau G factor, and this is what relates the electron total angular momentum operator with the electron magnetic moment. And also for zero field splitting, the states of the electron associated with different values of this had different spatial charge distribution, and so if you put them into some kind of Coulomb field, they will additionally split, and that's called zero field splitting. So now we go back to the nucleus. Nuclear magnetic moment comes from the motion of the protons and the neutrons, and for each we have the orbital part and the spin part multiplied by the corresponding nuclear magneton. So for orbital motion, protons are charged, and so a circular motion of a protein creates a magnetic moment and therefore interacts with magnetic field, but neutrons are not charged, and so neutron circular motion doesn't create a magnetic moment. For spin, proton structure is an unsettled matter, so even to this day there is no simple explanation for why this is the case, but for neutron it's negative, which explains nuclei with negative magnetogeric ratios, which are classically impossible, of course. So that's the neutron spin G factor. And well, at room temperature we are in the ground state, so we can use the same mathematics and a lot of mathematics later. Again, this is, I don't expect you to understand this, and I will not examine this. Let's just say after a lot of math it turns out that magnetic moment of the nucleus is proportional to the total angular momentum, which we happen to call spin, and that is where nuclear magnetogeric ratio comes from. And this mathematics is only simple like this for a nucleus with a single unpaired nucleon. If you have multiple unpaired nucleons, you have to do quantum chromodynamics, and for a lot of cases, even for something as basic as a deuteron, that is broadly an unsolved problem in nuclear structure theory, because the motion is so complicated and the potentials are just more or less unknown. Okay, electric multipole expansion, another flashback, right? Any arrangement of charges has a multipolar expansion. If you have your electrostatic potential, you can expand it in the corresponding Taylor series, and there will be the charge part itself, its gradient, and then its Hessian, and of course the sum of the second derivatives of the electrostatic potential is the Laplacian. The trace of the Laplacian is the local charge density, but if we look at pure electric field away from charge density, this is supposed to be traceless by Laplace's law. And then the corresponding energy has the straight monopole term, the dipole term, the quadrupole term, the octupole term, and so on. Now, the monopole term is just Coulomb interaction. We've already accounted for that. Nuclear dipole moment must be zero. This is because of the Pauli exclusion principle, or rather, no, this is parity symmetry. So if you invert the wave function, it can either remain the same or it can change sign, which means its absolute square must remain the same. The absolute square is probability density. For a charged particle, it's a charge density. Therefore, charge density must be inversion symmetric. This is why the dipole moment is zero. So there is no nuclear electric dipole. There cannot be. So the first electric multipole of the nuclei that does exist is the quadrupole. And those of you who do solid-state magnetic resonance know that somehow, mysteriously, nuclear quadrupole moment is rigidly glued to the direction of the spin. If you move the nuclear quadrupole moment, you also move spin. And the reason is the same. It's the Wigner-Eckert theorem that anything projected into the ground J multiplet becomes a spin operator. And so even though these phenomena are entirely electrostatic by their origin, the consequence is magnetic. So the consequence is an operator that acts on the nuclear spin. Exactly the same mass, we project the corresponding operator into the ground J multiplet. I will not bore you with the technical mathematics that is involved in here. It's horrendous, but more or less, roughly speaking, what we have is this is the spin state of the nucleus, and this is the corresponding nucleon wave function. So every spin state has a different charge distribution. And different charge distribution means different interaction with external electrostatics. And so essentially there are electrostatic splittings as the result to what is substantially a family of magnetic sublevels. So an electrostatic interaction becomes magnetic, and this is exactly how zero field splitting appears for electrons as well, right? So there's a direct analogy between the orbital structure of some lanthanide and the nuclear structure here. These are the same fundamental interactions appearing in a different dress. And then it becomes a nuclear spin operator. I will not bore you with all of this mass. Those of you who do battery materials will unfortunately have to become infinitely familiar with this eventually, but not yet. Okay, so summary of our whistle-stop tour of what normally would be an entire lecture course on nuclear structure. So what goes on inside the nucleus? The potential for strong nuclear force is unknown, but it is not unreasonable to assume that it is spherically symmetric. Spin-orbit coupling inside the nucleus is stronger than Coulomb interaction, so it dominates and creates those multiplets. Nuclear spin is actually total angular momentum of nuclear ground state. Chemists are always in that ground state, and to them, therefore, mu becomes proportional to J, magnetogeric ratio. If you do consider gamma spectroscopy where nuclear excited states are actually populated, then this breaks. Nuclear excited states have different magnetogeric ratio and in fact different spin. So the excited state of carbon-12 may have a non-zero spin, right? But of course it only lives for a few femtoseconds, so we don't realistically see that. Likewise, Q becomes a spin operator. And well, I've collected a few DOI links here for further readings on nuclear shapes, nuclear structure, and where all of this comes from. And it's also chapter 3 of my book on the subject, but don't read it yet. I think your year 3 as PhD students would be the right time to read that book when you are all comfortable with the spectroscopies that you are doing, because it's very easy to get lost in all of these subjects because there's just so much giant mathematical complexity that is sitting. I've sort of tiptoed you through the relatively uncomplicated things, avoiding quantum chromodynamics completely. But these are monstrous fields that one should not approach lightly. Okay, that's me for the lectures, and then we will have the class on, what is it, Wednesday. Another lecture and then the class.